All right, in this lesson, we're going to take a look at something called the ambiguous case of the sine law, or sometimes it just gets referred to as the ambiguous case. This only exists with sine ratios in terms of right angle triangles. The reason why is because the sine ratio is unique in terms of, and we've done this in previous lessons, if I said that sine of an angle was 1/2, and I'm looking throughout an entire circle, we know that's positive in quadrants 1 and 2, which means that the angle could either be 30 degrees or 150 degrees. Why is this unique to sine? Well, if I was using tan is going to be positive in between 0 and 90 degrees, or between 180 and 270 degrees. If I was using cos, it's going to be between 0 and 90 degrees and 270 and 360 degrees. Because all of this is based on triangles, it's unique to sine because the angle of 30 degrees and the angle of 150 degrees could both exist inside of a triangle. So if all we know is what the sine ratio is, then potentially there's two different angles that it could theoretically be. Now, there's going to be some restrictions that let us know it absolutely is this angle or that angle, but it won't always be there. So in some cases, we call it the ambiguous case because given certain pieces of information about a triangle, there's theoretically two different triangles you could create that fit the exact same information. And I know this confuses some people, but we'll get into it in a second. So, two students, Scott and Brittany, each constructed a triangle to represent the given information. So, what did they know? They knew that side length B was 4 centimeters. They knew that side length C was 6 centimeters, and they knew that angle B was 30 degrees. Scott drew this triangle. Brittany used the exact same measurements, 4 centimeters, 6 centimeters, and 30 degrees. And their two triangles look very different. If I use a ruler and a protractor to determine if they did it correctly, the answer is yes. They both measured out 6 centimeters and 4 centimeters. They both used a protractor to measure out 30 degrees. Both of their triangles match this information perfectly. What is the difference between their two triangles? Scott's triangle has angle C being less than 90 degrees, or acute. Brittany drew the triangle where angle C was greater than 90 degrees, or obtuse. It doesn't mean the rest of their information didn't match. It does. But in Scott's case, angle A was obtuse and angle C was acute. In Brittany's case, angle C is obtuse and angle A is acute. And the rest of their information matches perfectly. So, when it says, without using a measuring device, estimate to the nearest 10 degrees the angle of ACB, well, with Scott, it's going to be about 50 degrees. With Brittany, it's going to be about 130 degrees. Now, I would never ask you to estimate like this on a test. I would just ask you to use sine law, cosine law, or whatever in order to actually solve the lengths. So, it says, in each case, use a sine law to determine the measure of the angle. Well, for Scott's, if he's trying to solve for what angle C is, then sine of C is equal to C sine B over side length B, where sine of C is equal to 6 sine 30 all over 4. Sine of C would equal 0.75. And when I take sine to the negative 1, angle C is going to equal approximately 49 degrees. Brittany started the exact same way. But then when she got to here, she thought that C was obtuse. So 49 degrees was actually the reference angle. And she said that angle C was 180 minus 49, or 131 degrees. Both of their answers are correct. There's not enough information to tell us which is the correct one, so both of them actually work. The catch is that using those different angles of C, one of them is going to have a very big side length A and an obtuse angle of A. One of them is going to have a very small side length A and a very small acute angle of A. So how does this fit into when we're constructing triangles? Well, if I'm sketching out a triangle and it says that PQ is 3, PR is 4, and QR is 6 centimeters, I have a shorter side, I have a longer side, and I have a longest side. Where this is going to be 3, this is going to be 4, this is going to be 6 centimeters. Here's where Q would have to be, here's where R would have to be, here's where P would have to be to make this triangle. Now, is it possible to change around the triangle to create a completely different triangle? No. If I know all 3 side lengths and angles are in relation to their side lengths, I can't have different side lengths or different angles exist within the triangle. So it's set. If I know 2 side lengths and the angle that exists between them, where I know that I have an angle at Q, which is 40 degrees, I know that going from Q to R is going to be shorter. I know that going from P to Q is going to be longer. Can I create multiple different triangles based on this information? No. It's always going to be set. I'm going to say that this is going to be one measurement, this is going to be one measurement, and this has to be this exact angle. If I know two angles and a side length, this is going to be 40 degrees. This is going to be 30 degrees. Well, I don't even need to write the side length because I know that if that's 30 and that's 40, no matter what, the last angle has to be 110 degrees in here right away. So I can't have different angles. There's no possibility for new angles to crop up. Now, if I have PQR where it says that at Q it's 40 degrees. From P to Q, it's going to be, sorry, I'm going to do that in the other order. From P to Q, it's going to be 6 centimeters. And from Q to R, it's going to be 4 centimeters. Could I possibly create a different triangle? Well, I'm going to have the version of this where this angle is going to be obtuse, like we see here. But at the same rate, if I create an altitude in here, running along here, then I also could have made a triangle where it swung inwards 4 centimeters, has the exact same measurement of 4 centimeters, oh, sorry, I wrote the wrong one. This one is going to be obtuse. And it's going to be obtuse.